什么啊？
finite K algebra，这样我可以直接讲，这样它就是一个 finite dimensional vector space over
你有介绍这个字啊？
哪个
这个字
K algebra 有啊，在这个
啊
我们小 remark 里面啊。
好吧，如果你介绍就 OK 了。因为其实我为什么讲这样的东西，其实我就是要来 replace 掉这个字吧，因为我没有介绍那个字。
Yeah, that's why. But I think it's inevitable you have to use it. I think.
I mean 肯定你要 use it，因为
证明了这个是一个 K algebra，这样的话，我可以间接的表示 A 是。
因为你 prove 的这些东西好像是跟前面的跟我 tutorial 里面 prove 的东西是一样的。
对啊。
所以 that's why 我不想用这些字，所以我用那些 result 来 replace 掉这边的啊。但是如果你介绍就 OK 了，然后你自己证明哦。
意思是讲，我下面这里我已经 show 它是 finite K algebra，就是 K 是这个 finite K algebra。这样的话，我可以，这个是表示啊 A 是 finite dimensional vector space over 这个吗？
就对，什么？在选一粒吧。为什么你嘞？怎么你已经可以这样写了呢？
不这样写。
等一下我看一下，我们先开课，
OK。
等一下再跟你讲。Hello, testing. It's all of you here yet. Most of you. Okay. I think I know that a lot of you. 哦，有意思呢。就好啊，他去哪里？哦，so I think a lot of you have some problem in reading your stuff, is it? Okay. Later I'll let Siyu come and share how he read so hard stuff, like how he understand the hard stuff in general. Can or not, Siyu? Maybe you can share about how you study your FYP. Okay. Why I asked him to share because I started, so he started FYP with me like half a year ago, and then he picked a really hard topic. I also don't understand that topic. I also not working in that field, but in the process, we try to decode the paper stuff, and then I think he got quite a good understanding. Not very detailed, but at least can get a big picture, the connection. And maybe you can share how to like get a big picture when you read. Yeah. Later, okay, when they start to sleep or in fact you. Okay. Okay, so what can you do with a maths degree? You can be a pop. Okay, so if people ask you, 读来做么？数学读来做么？What's use? Study maths. You can be a pop. Yeah. Okay. So your pop is a bachelor in mathematics. Okay. Okay, so we will continue with the story of category, but still I want you to bear in mind that maybe category theory is a jargon for you, but really we will study it from the property, okay, that we learn from these polynomial method. Okay, and then we just create a language, okay, to describe everything in a system. Okay, so let's recall what we had. Okay, so let's recall what we had last time. So there are two categories we are interested in. Okay, there are two categories. So one is category of what affine algebraic set. Okay, and what's the map? So last time we say that category have two data, right? So one data is object, okay, the other data is morphism. Okay, so what does morphism do? It need to be what? What does morphism do? What does a morphism do? Sorry? What does a morphism do? Okay, you can think of it is as an arrow between two objects. Okay, arrow. Okay, and then the property of arrow that you need to satisfy is what? You can compose arrow. Okay, you can compose arrow. So obviously the two things inside your AP will call it domain and codomain. Depend on where you start the arrow. Okay, the place you start. Okay. So what I want to say is this morphism here, you can think of it as an arrow from A to B. Okay, so the starting of this arrow is a domain, and ending of the arrow is codomain. Okay, and then you must be able to compose arrow. Okay, after composing arrow, what do you need to do? You need to have an identity arrow. Okay, what's the identity morphism? And then what else? Is it that's all? Yeah, I guess that's all. You need to compose. Oh, one more thing, associativity. Okay, so associativity is quite important. Okay, it's a basic group definition. Group you always assume is associative, right? Okay. So two things we learn here. So category of affine algebraic set, and then with morphism, that is polynomial map. Okay, obviously this map is you can compose. The composition is associative. You should have identity, morphism. Okay. The other part is category of finitely generated, reduced K algebra. Yeah, obviously the map here we consider are just K algebra homomorphism. So why finitely generated? Why reduce here? Do you remember when we learn commutative algebra? Finitely generated refers to what? Huh? Finitely generated related to Noetherian ring. Okay, and then reduce. Reduce means what? Reduce algebra. I think we just introduced last week. Reduce algebra means what? There's no torsion element. Okay, there's no nilpotent element. Okay, there's no element such that it is non-zero, but some power of it is zero. Okay, so everything is reduced. Okay, or not? Okay, so reduced here would refer to being radical. Okay, correspond to radical ideal. Radical ideal says what? F is in the radical if F to some power is living in the ideal. Okay, so I have a example. Have a tutorial question inside tutorial 4 already, I guess. 4 or 5. 5th week of 4th week already now. Last week. Tutorial 6. No. We need to reduce by 1, right? Because first week we have empty. So I think tutorial 5 so there are questions on radical, so try and do it. I think in the assignment I also have two radical question inside. So try and get familiarized with this radical ideal. I think I remember one very interesting statement is if you take radical twice on an ideal, what do you get? Just the radical. So square root I equals to square root I. What's square root? The different number. Okay. Okay. Right. So two things here, right? So what's the map between these two? Okay. So to talk about the map between these two, okay. Well, so I will have V here, right? And then on one side, what we associate to V last time? The coordinate ring, KV. What's KV here? Polynomial ring portion by the ideal attached to V. Okay. But similarly, last time we defined something called pullback. So meaning if you have a map between two alpha algebraic set, you can define something called a pullback. Okay, so pullback go from where to where? There's one thing I want you to remember, right? If you do pullback, it will define a map on K algebra, but on the reverse direction. So KW to KV. Because you pull the function, okay, in KD back to W. Because you start from did I do something wrong here? Huh? Did I do something wrong here? Wait, let's check. Huh? Sorry? Did I do something wrong here? So let's check. Yeah, sorry. I should start. Oh, right. So my function, if my function go from W to A1. Okay, so first of all, okay, I think there's one thing you need to remember also. So if you take phi from this coordinate ring, okay, do you know that this phi here actually is a map from V to A1? Right, because you just evaluate. You just points of V into X1, Xi. So what do you get in the end? You just get a V1, A1K. Does it make sense? You need to think of, I mean, a calculus example is useful here, right? For example, fx equals to s squared plus y squared, for example. Okay, maybe you can think of it on the zero set of x squared plus y squared minus 1. Okay, so if you substitute the point here, okay, that make x squared plus y squared equal to 1. Okay, into this function, what do you get? You always get 1. So you can see that this function is not constant. Okay, it's not constant on okay, so here is two variables, sorry. So I should put fx, right? It's not constant on two-dimensional affine space, but if you restrict to this circle here, become constant function. This is something people study in functional analysis. Okay, non-constant function, but you restrict to some domain, become constant. Yeah. Does it make sense? Okay. Okay, so yeah. Okay, so you can pull your function back to V. Okay, if you start with a function in KW using G. So what do we do here? We send object from one category to the other category. We have a map that send function, okay, in category to the other category. Okay, so what we get here is what we call a functor actually. Where is it? So we will quickly go through this category part. We won't spend much time, but I can tell you this phenomenon here. Oh, where's my category stuff? Okay, so what we have is we define a functor. Okay, so functor is like function. What does function do? Give you an input, give you an output. But functor need two input. Okay, one input is object, the other input is morphism. Okay, so Input an object, give you an object. Input a morphism, I give you a morphism. Okay, so this is functor. Okay, this is what functor means. Okay, so it's a map between the object and then map between maps. Okay, but there are two kinds of functor here. One is covariant functor, one is contravariant here. So what does it mean? So what does it mean here? Can you notice 来，现在什么都没有教叫你看不了，看你的观察力好不好这两行字什么差别 ？Okay, everyone observe that or not? One, when you map forward. Okay, so when you map from a morphism of C to morphism of D, so first of all, you are function from A to B, but after mapping, you are mapping between F A and FB. But the second one, you are morphism between A and B, but when you map to a morphism in D, it becomes a map from FB to FA. It's somehow going backward. Okay, so this is what differentiates covariant and contravariant. And so contravariant is backward. So in our case, our funder is covariant or contravariant? Contravariant, right? You see, so in our case here, you have a map from B to W, but when you map forward, it becomes KW to KV. Okay, now, but the map of object is what? V to KV, W to KW. So it's swap, the arrow swap. Okay, now. Okay, does it make sense? So let me draw something for you. So V, you map across become KV, but W, you map across become KW. Okay, but you got a map between V and W, you map across become going backward, G star. Okay, if it's contravariant, then it will go this way. Sorry, covariant. Okay, so if it is covariant, it will follow the same direction of G. If it's going contravariant, it go yeah. Okay. Does it make sense? 有问题吗？没问题，有问题吗？金盛，金盛有问题吗？金盛，没问题，听得懂我在讲吗？大概，要不要重复一下？Do I have an example of covariant functor? Sure, sure. But I think it's not important for this class. Maybe you can consider identity functor. Very obvious one. I think forgetful functor also works. Okay, forgetful functor just says that you map your category into a category of set. OK， 一个是往上往下，记住往上往下的差别。OK， it is the same direction with the original G, then it's called covariant. The other direction is called contravariant. Okay, but okay, yeah, there's some property to satisfy here. There's some property to satisfy here. Okay, so if you map identity across, you get identity in the other category. And then if you map composite across, then you will do the swapping direction also. But did you notice or not? This is the property we prove on the pullback. Identity star is the identity on the K algebra. And then GF star is what? F star composed with G star. This is functor. Okay. Okay, so let me add on here. So we actually prove that identity star equals to the, let's say identity star on W is equals to the identity KW. And also, if I put FG star, we also prove that it is G star composed F star. Okay, so the proposition is we have a contravariant functor between these two. Okay. And then you should ask the question, can we go backward or not? Now, obviously we can. Actually, we proved that we can go backward, right? I mean, for here to here, I think it's okay. Okay, because you just have an IV here, right? Become your variety. But here, go back here, actually we prove it for every K algebra that exists a polynomial map such that the door is equal to this as unique also. Actually, we can go backward. Okay, so going backward. So the question asked now, no, if I compose these two functors together, do I get identity or not? Which is the identity functor? Do you get identity functor? Okay. Surprisingly, in this category sense, not always equal one. But what we can do is show that they are isomorphic. Two functor is isomorphic. 想象得到吗？有想过 two function is isomorphic？ 对，讲答案了。没有想过哦，两个 function as long we only think about two function being equal. How to check equal? Check a point. But what does it mean by two functor to be isomorphic? Okay, so we need third level of map. Okay, the third level of map is or second level. Second level of map is called natural transformation. Okay, so we need a map between functor. Okay, so what does it mean by a map between functor? Obviously, functor you also cannot check, right? So you need to evaluate your functor first. So meaning what? Meaning that you need to define every natural transformation on every FA to FG. Every FA to FG. Because F and G functor you need to input something that you can study. So now you need to input objects. Okay, so you need to define a phi for every A actually. Okay, between FA and FG. Okay, so it turns out that you can do you can define a transformation between F and G, which we call these which we call what? Which we call that such that when you compose them, you get an isomorphism of between the identity and the composition here. Okay, so this G and F here is the functor we started with, and this isomorphism here is given by this kind of field. Okay, so you need to produce actually. Yeah, you need to produce. Okay, so if you can get this isomorphism here, so how to get isomorphism here? So once you define an epsilon going forward, you need a eta going backward. Okay, such that when you compose them is the identity on functor. Okay, so it's the identity natural transformation. Okay, yeah. Okay, identity natural. So it's like ladder, you know. You know what's ladder? You know what's ladder? Climbing ladder. So you have object, okay, you have morphism, but between morphism you build a functor, and then between functor you build natural transformation. So you could imagine we can play induction. Hey, yeah, true. We can do induction. Between natural transformation, we have something else. What's the name? Anyone can recall? Okay, so so between functor is morphism, right? Okay, and then functor is two morphism, and then natural transformation is three morphism. So between three morphism, you can build a four morphism, and then five morphism, six morphism, seven morphism. And if you put all these things together, actually, there's something called infinity category. You study all these morphisms together. You can go online search infinity category. There's a lecture by Emily Real. They're trying to teach infinity category to undergrad. Yeah, infinity category. 所以你看，人家大学已经在做 infinity category 了，我们大学连 epsilon delta 都学不会。我没有怪你们，我怪你们的老师。我没有怪你们，我怪你们的老师。Okay. But anyway, So yeah, so not very important, but I put the detail on if you want to study. Okay, it's not important for this course either. But what I want you to know is this equivalence here. Okay, this equivalence here. This equivalence is what we have. Not equivalence, but the contravariant factor. Okay, this is the part I want you to know. This is just a contravariant factor. To prove equivalence, you need a natural transformation. But from this functor, you can kind of do the equivalence already. But the takeaway is with this functor, you almost get your equivalences. Okay. Okay. So how they correspond is very important. B and K, B, and then and the fullback of that. Okay. And then one thing I want you to appreciate in this course is you are already fortunate than the 2209 batch already. They already want to graduate already, only they listen to this. So during their FYP, right, they also do this thing because they're doing with me. Because my staff are using this language here. So they have to read themselves. Okay, but you guys have a proper course, okay, to check, to read, okay, to study. Okay or not? So I hope that even later batches will be more fortunate than you. Okay, maybe they can do more category theory, they can do more representation theory. Huh? On what? Yeah, they could have a class on this. Yeah, or maybe, yeah, it's an ME course, I guess. ME course. So I have an idea is like this. I'm not sure whether Tao Shen will accept it or not. But my idea was we put out as many ME courses as possible. Okay, maybe in a 2-year rotation. So what does it mean? So meaning if you do undergrad here until 3rd year, right, it's not enough for you to finish all the ME. You need to stay here and do master. I think this is a way to generate income also. Correct or not? So we line out all the ME courses. Okay, you cannot take it, you cannot finish it in 3 years. You have to do master so that you can finish all the ME. Then you are pretty good already. You could get to most of the field knowledge in most of the field. Yeah. Because their thinking now is very rhetoric. So what does it mean here? Since undergrad can take all these courses, then that means their master no need to do anymore. So I restrict undergrad to do these ME courses. Very rhetoric one. I say cannot. You should put up even more ME courses. Yeah, so that they can rotate. Make sense or no? I ask you, make sense or no? Does it make sense? Does it make more sense or no? Okay. There's so many things to share, so many knowledge, so many field to share. But they try to like cut. This prove one thing, you know. Actually, this prove one thing. Can you think of what this means? Huh? You know what? This means they have nothing to share. Because the courses here is not enough for me to share, you know. It's not enough to learn. They still want to cut. There's nothing to share, obviously, nothing to do. But for me, there's a lot of things. Still got a lot of more things to do. They still haven't do it. Yeah, so one thing I want to plead you, okay, maybe 要跪下来求你，求你们好好学。So please learn it properly. Prove to them you can do it. Otherwise, they will use you as an excuse, you know. They say 学生都学不会的，讲听不懂的。他没有一句是讲自己的哦。他没有一句讲自己哦。他没有一句讲自己教不好什么我要讲进步没有了全部怪别人了 我很奇妙，奇怪，那种人很奇怪，奇怪。因为啥？This is life. You have to deal with this kind of people always. Okay, never mind. Okay, so we will continue. Okay, so this part I guess we finish. So we'll continue with rational maps, polynomial map. But we go even general. We call it rational functions and maps. Okay, so please don't be confused. So far we already met polynomial function, polynomial map. Okay, so now we're going to introduce fractional function and rational maps. So later on, you will see this word coming up again, but with a different domain and codomain. So please be sure what we are talking about. Okay. So now we're gonna fix a V as an affine variety. Okay, so meaning we are considering the irreducible affine algebraic set now. In this case, the polynomial ring here, the coordinate ring here will be integral domain. Okay, so what does rational suggest you here? Rational number, you will be dividing by some non-zero thing. Okay, so in this case here, we will also consider the field of fraction of coordinate ring. Okay, so we'll consider the field of fraction. So this construction here is pretty general. As long as you have an integral domain, you will build the field of fraction already. Correct or not? You will use it as your domain. Sorry, the denominator. Okay, define it. You have a well-defined denominator here. And well-defined fraction. All right. So what is field of fraction here? Okay, so let's define what's the field of fraction here. Well, I mean, we will call it function field. Okay, this is the main point here. So previously we just have coordinate ring, right? So now we will have a function field of V. It's actually the field of fraction of KV. Okay, so we denote it as a K round bracket V. And then every elements here, we will call it a rational function. Okay, so how does it look like? So let's make a remark here. So let's see how it looks like. So how it looks like here. So let's make a remark here. So any rational function, well, it should be able to be written as f equals to g over h. So where do we pick this g over h from? Obviously, they are from k, kb. Okay. So it's like the rational numbers, okay. So this kv here might not be ufd. Okay, so let me put here. So in general, k adjoint v need not be ufd. So actually such representation is not unique. Okay. And then f only well defined when f is non-zero at that point. Okay, so let's define this. So let's call another name definition here. So if you consider any function in the function field of V, and if you pick any point in V, and we will refer that this rational function, okay, because this is an element in the function field, is called regular. Okay? This is a pretty important adjective you need to learn. So regular at P, if there is this representation F equals to GH with HP not equals to 0. Okay. So we will consider any function as regular if you can write F equals to G over H such that this denominator is non-zero in P. At P. Okay. So this regular definition, right, is very specific to a point. Okay? It's very specific to a point. Okay? Very specific to a point. Okay, so domain here. So you see, HP not equal to 0 also means what? Actually, H is not in the ideal defined by P. Okay. Okay. So next thing is we define the domain of definition, which we write dom F here of F. So what's this domain here? So this domain is just collecting all the points, defined as collecting all the points, okay, in V such that F is regular at E. So we just look at all the domain that makes it regular at P. Sorry, all the domain of F such that you can write it as G over H, and HP is not 0. Okay, all the P that make this representation work. For the next part of the proposition, right, we want to make this further definition here. So for every polynomial function H in KV, we will define VH such that all the point in V such that HP is not 0. Okay? So you might think that this VH is trying to capture all the points such that H is not 0. Okay? So the previous case is all the point in V such that H can be written as G over H, such that HP is not 0. Okay. So dom F has more property, more things than VH here. Okay, because you need to write F equals to G over some H. But this VH is a specific H. You already fix some H. Sorry? Say again. Support of H. Okay, I cannot make sure because I'm not sure about the support definition yet. Maybe can, but I'm not I cannot confirm. That's all. That's all. Do you need like non-zero at certain interval or something like that? On it. What's the definition? I mean,
Full set of the set which fx does not equal to 0.
that's all.
Yeah, that's
Okay.
it's like definition is just like that. But if you have a topology, then it's really fine.
Okay. Okay. But anyway, something that make your F not 0. One proposition you can prove is VH is an open subset of V. Okay, this is quite easy to prove. I think last week we did general topology, right? You should use a general topology argument. The complement of Ivan, what's the definition I keep asking you last week? Huh? General topology. AC is good. Okay, so the other way around it. A is open if AC is closed. So you want to show this open, right? What is the VHC? Yeah. VHC 0 that satisfy HP equals 0. So it's a closed affine algebraic set. Wait. Oh, right. So let me see what's going on here. So this open subset here is just mean that, okay, this open subset is quite, this is not the subspace topology. This is just open, I think open set as a subset of V, that's all. This doesn't mean subset. I mean, subspace topology are almost useless. Almost useless. We rarely use subspace topology unless you just want to study that subspace. Otherwise, what does it mean by non-open thing? You want it to be open, right? Last time we want the half-closed interval, right, inside an open set. But if you consider as a subspace topology is open, but why do you want it to open? If you want to study the whole space, okay? Only when we want to study the subspace it becomes very open. But rarely we did that. Yeah. I think the open subset here just means open set as a subset of. No subspace topology. Yeah. Okay, next. What time is it? Okay, good. I think we should prove this. Wait. All right, let's prove this. So we'll prove a characterization of domain of a rational function. Let's see what does domain of rational function do. Okay, so first of all, dom F here would be open and dense. Yeah, open and dense. Function how the characterization of. Yeah. Okay. Characterization. Okay. So dom F is open and dense V. And second, if you have a dom F to be equals to the whole V here, okay. So meaning you can write it as F over G for all the point in your V. Okay, so this means what? If and only if actually your function is just a polynomial function. Right? It's just polynomial function. It's not living in the field. There's no denominator. Makes sense, right? You cannot have one denominator that works for every. Okay. Later we'll prove it. Okay. Yeah. You mean does this require K to be algebraically closed? Seems like no. Seems like yes. Actually, yes. Actually, yes. Actually, yes. Yes. Yeah. Later we'll use Hubert now. Wait. So proof number 2. Yeah, we need it. We need it. Yeah. So here, maybe to be sure. So I think from the noun stanza onwards, right, we will assume K to be algebraically closed. Yeah. From Hilbert noun stanza onward, we'll assume K to be algebraically closed. Algebraically closed. Yeah. Okay. Yeah. Yeah. Otherwise, how we build the equivalence? Yeah, we need to build the equivalence. We need the algebraically closed stuff. Okay. Third, if your DOM F contain VH, okay, the VH we defined just now, all the point that make H non-zero, then actually you can write your F as a polynomial function, okay, potentially adjoin the inverse of H. Okay, so divide by H. Okay, potentially divide by H. Okay, so let's prove this. Okay, let's prove the first one. So before proving it, we will define one more thing. So let's take a rational function here. So we'll define an ideal of denominator of f. Okay, by df here. So what's df here? So df here is all the h in a polynomial ring kv such that h times f you will stay in a polynomial ring of kv. Make sense or not? Okay, if your f have representation of g over h, right, then you multiply by h, you will stay inside the polynomial ring. Okay, so we collect all these h. Okay, obviously this is a subset of kv because we pick element from kv. So by definition, so what does this df produce for us? So this df actually is all the h in kv such that there is a representation f equals to gh. Okay, more than that actually. Okay, more than that, what's the thing that you need to put it here? Something you multiply to h f, and then stay inside polynomial ring. There's one more thing you can put here. Huh? What's the thing? Huh? 0. Okay, because you cannot put g divided by 0, right? Okay, so you need to treat 0 differently. Okay, and so df is this, and what can you consider here? You want to show that DOM f is open, right? So you can look at the complement of this set here. Okay, so in this case here, this open in V is the subspace topology, open in V, right? Okay, so if you look at this complement here, what is this? If you throw away the point in DOM F here, obviously still the point in V, but what does it satisfy here? I think just now we talked about it, right? Now we talked about it just now, right? Oh, just now we talked about VF. How about here? If we throw away DOM F, now what's DOM F? All the P such that you have such that your F have a presentation of G over H such that HP is not 0. More general than your VH. Okay, more general than your VH. So what? So you can be written as HP equals 0 for all hash in. Actually, df. Okay, df, we use it here. Okay, so meaning what? Meaning this is a affine algebraic set on df here. V of df. Okay. All the point that make df0. That's why we realize this complement here as some closed set. Okay. So DOM F is open. Okay. How to show it is dense? How to show some open set is dense? Last time we introduced the true equivalence on irreducible space, right? Okay. What's the true equivalence? Definitely equivalence statement on irreducible set. We haven't introduced this in general topology yet. Okay, but we just introduced it in this class. There are three equivalence property on irreducible set in a topological space. So if V is irreducible, meaning what? One of them is every open set is dense. So meaning if you once you prove that this is the open set in an irreducible set, then it is dense already, automatically dense. Okay. Otherwise, you will find two open set such that their intersection is, or every two open set inside your irreducible set should be intersect always. Okay, so maybe I'll remind you a bit. Quite important. Because later we'll keep proving something is dense in algebraic topology here. After we did Zariski topology, I think. Yeah, this thing here. Okay, so you need to remember how to prove some open set is dense in an irreducible set here. Okay, so please remember this. Once you have V is irreducible, any two open set in V or V, they must intersect non-trivially. Okay, and every open set should be dense in V. Okay, otherwise you should be able to break up your V. Okay. Okay, no? Okay, ma? So actually, this tells you how to not break up. Every two open set must intersect. 是吧？对哦，对哦。The other open set should be able to build out the other space. Any open set. 是吗？ Is it true? This is what irreducible means. Okay. I think I like topology a lot. There's a lot of philosophy inside topology. Life philosophy. Very important. Okay. So since DOM F is open in irreducible V, DOM F is dense. Okay, so it's a result of open in an irreducible set. Okay, I think let's do it for the next two part. So the next two part actually is quite simple, but the meaning is quite deep. Okay, so let's say DOM F is V. Yeah, just now computation, right? V/V equals to VDF. So meaning what? Meaning what? Your VDF is empty. V of something is empty. Still remember or not? Last time we proved. Last time we used Z okay? But now you need to swap between Z and V. So the zero set of some ideal is empty. Meaning what? The ideal you started with is actually the whole space. Okay, so meaning what? The unique element is in DF. So this part is by Hubert Salazar. So this is the part that you need the algebraic close. Okay. Well, one is in DF means what? One is in DF means what? Okay. What is DF? DF is this thing, right? Okay. Hash such that F hash is in KB. But one is in here. So F1 is in KB, meaning what? F is in KB. Okay, so this one implies that hash is in. Cannot. DF is all the hash that make hash. DF is all the hash that make F hash inside core memory, but one is in there. Or F times one is inside. So in particular, F is inside there. Okay. So if I want to be precise, I write this as F equals to F times one. Okay. Okay. All right. Last one before we break. Suppose we have DOM F containing VH here. Okay, so what does it mean here? So this is true if and only if VDF is equals to V slash DOM F, which is in turn a subset of V slash VH here. Okay, so using the previous complement now. Okay, using complement. What does this mean? What does this mean here? VH is what? All the points such that HP is not 0. But you take the complement, meaning what? H will become 0 on this point here. So meaning what? Meaning H vanishes on the point VDF. On the H here will vanish on the point of VDF. Okay. But again, here we will use NgeKieSeng here by Hubert NgeKieSeng. So how are we going to use Hubert NgeKieSeng here? Just now you are using the weak one, right? Okay, now we're using the strong one. Okay, so meaning what? Hash to some power n should live inside DF. As is an n such that hash to n is in DF. Okay, but what does this mean here? This means that your F should be able to be written as G of some hash to the n. Okay, in K adjoin V. Obviously, now we need to adjoin. Okay, so by the definition of DF. Okay, DF is what? All the hash that make F hash a polynomial function. So if you multiply hash n to F, you will get G, which lives inside V. Okay. Okay. Maybe you might think that this proof quite elementary. Okay. Actually, very hard because you go through a Hubert NgeKieSeng and also using some complement stuff. This three proposition here will make up something very important thing in a category here. Okay. So later we'll introduce it. Let's break until 5:08. 啊，不一定啊，就不一定啊，它只是 general 的 algebra 吧，不一定啊，general algebra 不一定，不一定啊，general 吗？我叫周末不能，你可以找一个 example。没有啦，就是 I mean，那就像我们 proof 的，其实我们 proof 的东西啊，如果你把那些 y 啊，其中一个 y 丢进去啊，它就不是。课本写什么？课本写什么？课本写什么？你 final algebra 跟 final general algebra 不一样。
Finite algebra 的意思就是
finite
modular space。
对，
我没仔细我写的东西，你看我这边有一个栏，这边有个框的，看到没有？我定义了什么是 finite algebra，因为书上面。那你是框小？哎，那是因为我一开始别给我把这本子这样子容易断。哎，这个地方是因为它书上全部在用 finite algebra 这个词，然后后来我就懒得改。我一开始把这两个东西弄混了，然后我刚中间我才发现这件事情，所以赶紧补了在那些什么。Finite algebra 不等于 finite generated algebra。哦，
够力了。
Finite algebra 的意思是它是个 algebra。
So that's why 我把它叫成 dimensional vector space。
对啊，
我不想这样。
你那个说话有一个问题，理论上来说 vector space
对，但是我的意思就是 ，OK， 等一下我要澄清这件事，我要澄清这件事。
按理说它是个模具，不是？
你看我要澄清，
vector space。
我要澄清。OK， 等一下我要澄清。
而且是 R 之外的一堆 variable， 有限的 variable。Finite algebra 我可以写的。说白了就是 finite generated 你的这个 adjoint， 不然就是 algebraic adjoint， 但是 finite algebra 这个 adjoint 你只能证明你的 adjoint。Yeah, do you see the difference here？
我知
啊，你发现这个是
This is
对，它是 algebra， 但是我们在这个地方
是有乘法呀，
有，但是我们不能用。algebra 一定是个模具，对不对？因为 algebra 是模具加了乘法的结构。我们在说 finite algebra 的时候，我们不能用这个乘法结构，不能用这个向量乘法结构，我们只能用 scalar multiplication。
这个情况是怎么？
就我们在做 adjoint 的时候，不能对这些 adjoint 做那个乘法结构。
你想看有？
不是，它有乘法，只是我们不能用这个乘法来构造出新的东西来。
just having a same analysis, yeah, because they are almost
但是做完了
对，所以为什么你还要分 cases？
不是可以做 x 出来，就比如说 K 加 x， 你是可以做 x 乘 x， 你得到一个新的东西的。但是如果
没有，你可以看不到，但是你应该写了过后，应该要发现好像
这个 x square 我不能用 x 乘 x，
其实前面也有这个情况在啊，
前面有那个 scalar。
所以就为什么会不一样 argument 不可能不一样。
你自己多问写的东西
一样啊，
我都已经把书上的东西翻译了。
对啊，就是应该是一模一样，因为如果它已经出现了，
一直在重复，只是我 relabel 嘛。
不应该呀、不应该这样嘛，对不对？就不应该这样哦。就是如果真的要分 cases 的话，那些 cases 应该是不同的 proof 啊。你看一下能不能再写简单一点？你看一下能不能写单？如果不能，可能是我错，你要去 check 一下。你看一下是不是真的不能分？
这一个是这一个，但是这个是这一个微信有什么？对，这一个就是纯这一个，就是说每一个 A 每一个写在里面放进去就这样。这一个就是 algebraic 的 definition。所以这里会有 ax square 那边，这里就不会有 ax square。
我不知道 B 里面有没有 A1 啦。
来先，
哇，谢谢。你喜欢这个是不是成题？
所以 A
因为A 确实就是这个牌子，好像。
就是那边买，
对，
鱼湾那边。
你想为啥？我本来想买一包，
因为在我房间里面 做什么时候我们就定说你所以在这里，
对，是吧？
因为我就是那个时候发现这个治疗系统。哎呦，我怕你
对
干嘛？
你那个是按照本听的，对不对？
这个怎么说？我能写 A 为，对，
其实我在想有个问题是，你的东西越想去不
但是我 A 里面东西还是很多，只是我听了我就觉得是
有问题是越确是不是 L 字？现在这个东西不一定是 L 字。你只如果说四个嘛，四个说不好，四个是它的。
我不要管说，
没有问题，就是你这个东西不一定是 L 字，你只
Hey, we got the 4 minutes, right? Maybe you can ask Siyi come here. Maybe you can share something. 啊，现在也要上课了。So if you are wonder, right? Okay, when you do project, do research, you don't understand, a lot of things don't understand. You can try listen to his experience. Do you understand anything or not when you started your FYP project?
Because even now, I couldn't understand all of the research that have been done by them, but what I have learned is like when you're trying to learn something very deep, right? When you look at some research paper, then of course you need to like go to their introduction, and the main content is not like really very important unless you have a lot of time, then you can go through it. But the introduction is very important, and because it gives you like how the process going, and you can roughly like get the picture from the introduction. And of course, in one particular research paper, they'll cite a lot of resources, and of course you can't understand without reading all of the resources, but you can try to like find you can use the resources that cited by them, and then you can further your research, and that's how I do. And of course, when you start on one particular problem, you don't you need to continue, like if you really don't understand them, then just leave it first, then you continue to see like how you can go behind first, then you can look how they actually link what you don't know to the thing behind them. You can see, you can get something, you know them, yeah. And of course, you need to like find a lot of resources when you get into a new field. I mean, even a new notation, maybe even one reference is not enough for you to understand its definition. Then you need to find more resources to support you. And of course, you can consult your lecturer. That's another important thing to do. Yeah, I think that's it. I think that's.
Okay, you got question for him or not? You get start, then how you continue? You got question for him? NgeKieSeng. Okay. So you know what's the thing he's reading on? Yeah. Anyone know what he's reading on? He's reading on the paper that I shared to you that get the breakthrough prize last time. The proof of the geometric Lang conjecture. So he's reading on this thing. So if you go and view PDF, you can go and view it. For free one, this one no need to pay.
This thing that you say is a connection between representation theory and algebra.
Yes. So if you go see, you see, once you see this, you immediately throw this paper already. Is it true or not? If you see all these notation plus notation, the subscripts are more. Why got a half there? Can I put 3/2 there? See? If you see this paper, what's your reaction? What's your reaction if you see this notation? Wow, so many superscript, subscript, some more. All these adjective means what? But I would say that from the first day until today, he already learned something more than what he started with already. This is the very important thing in research. Day by day, you learn a bit more, a bit more, a bit more, a bit more. It's not about what you don't know, okay? But sometimes it's perception. This perception. Perception. It's perception. 有人讲我很坏 I'm very bad. I'm a bad guy. Why? Because I let you know what you don't know. I let you realize what you don't know. Okay? Sometimes this is quite demotivating. I agree. Oh, thank you. Thank you. Sorry. Thank you. So sometimes it's quite demotivating. So I'm trying to get through this. At the same time that I made you know that what you don't know, at the same time I made you learn. This is my homework, or maybe. Yeah. Okay. Yeah. Okay. No. Yeah. So while I'm learning, maybe you need to how to say how to say need to adapt to my style also sometimes. Yeah. For sure. Okay. For sure, I will make you learn something that you never know before. For sure. Okay. Yeah. But it's hard. It's hard. It's really okay. But well, if you do gym, you do sport, then you understand. It's very hard. Okay, it's very hard, very tiring. And if you study maths not tiring, then something wrong with you already. Okay, no. In particular, maths is a brain exercise, so your brain must be tired. Very true. Can you go back now? You still have how many more? 39 minutes. Yeah. So you need to train. Okay, need to train one. Sport person also need to train one. Okay. This is what they call what do they call it? 哇，很久没有运动了，忘记了字叫什么？可以持久这样吗 ？Yes, stamina. Okay, you need stamina. Okay, do max also you need stamina. Okay, yeah, stamina is very important. Okay. Yeah. Or what? Oh, okay. Yeah. I guess it's a complement of a course. I think it's open in both, right? Because wait, so VDF is I think we just view V, I guess. Let me think. So V of DF. Okay, I think we just view V as a topology space. Yeah. So you see, so we don't need to care about subspace topology even, right? Because we just treat it as a topological space. So that's why I say that subspace topology is quite useless sometimes. Okay. Because sometimes when we want to talk about subspace topology, we really treat that whole space as a topology already, topological space. Yeah. So there's no need to talk about subspace topology. When do we need to talk about subspace topology? Is when we want to talk about the whole space and the subspace together at the same time. But now, not really important. Yeah, we don't need to care about the affine space really for now. Okay. Okay. Wait. Let me continue. Okay. So let's continue. We named the next section called the structure sheaf. Yeah, but we will not introduce the sheaf property. Okay, but we will call something as a structure sheaf. Okay, yeah. So it's a different approach. So if you read Hartstrong, they will tell you what is the structure sheaf, what's the property, but they never tell you what's the object that structure sheaf really is. But now we will tell you what is the object that we call it a structure sheaf. And then from this object, and then we generalize the property on this object, and then we have a general definition of structure sheaf. Okay, but we'll define what is structure sheaf now. So it's really motivated by the previous theorem there. So in particular, part 2 of that, let's do a motivation here. So from previous theorem. Okay, so the part 2 says what? The part 2 actually says that the polynomial function are precisely the rational function. Okay, are precisely the rational function that are everywhere regular. Okay, so in mathematics, this kind of statement is very intriguing. 很有趣. For example, in complex analysis, right, you also have some statement on everywhere complex differentiable, everywhere holomorphic. What's the statement? Anyone remember some very interesting result from complex analysis? Then what the function should be? And I did so any theorem on those kind of function or not? Huh? If it's everywhere holomorphic, then it's a constant. Okay, okay, yeah. And then I think there's also a very important result in like PDE or the differential equation saying that maximal principle.
Yeah.
What does maximal principle do? Or just achieve one maximum, is it? And within a bounded set.
Actually, the maximum principle says it achieve maximum at the bounded. But if you achieve maximum inside, then it is a constant.
So if you achieve, so you mean okay, so you mean the function must achieve, what's the function considered there? Any function? Harmonic function. Okay. Okay, good. So you see, this function put some adjective and then check some domain then there will be some result coming out already. Okay, so this one actually very similar to the complex analysis one. Later we'll prove a similar theorem. Okay, saying that some function space must be always a constant function. Okay, so right, so it's every regular. So hence from now on, we will refer to polynomial function as regular function. Okay. So polynomial function is always regular. So regular function include polynomial function. Okay. Well, so next. So in the following, we will define the ring called all U. Okay, all U. So all U here. So the ring all U of function regular on an open set U. Maybe. Okay. Oh, before that, for the assignment 2, right? I write finite dimensional vector space over a ring here. So Why I do that? Because the vector space, I literally want to replace the field in the vector space into any ring. There's a technical term for this. Actually, it's called module. Yeah, but I haven't do it yet. But actually, I will do it soon, later. Okay. In fact, in retrospect, I should do it first. Then I don't need to go through this terminology. Okay, so if you are confused, right? So vector space over some ring, right? Usually, what I meant is I replace the field with other thing. Okay. But I think to be precise, I should use module. Okay. Okay, so we define OU already. And then next, we'll use this OU to define what's the structure shift of a variety. Okay, well, so with this OVOU here, let's see what we can do here. All right, so first thing first, we will define the local ring. So what's local ring here? So we will define actually the ring of function on V regular at a point first. Okay, at a point. So OU is a ring of function that's regular on the open set, right? So we start with point first. Okay, we start with point first. So what's the local ring here then? So the local ring here is defined to be, so the local ring here really suggests locally. So we look at the point. Okay, so local ring of a V at a point P in V is the ring. What do you think? What do you think based on what we have constructed? These are actually all the function in the function field such that F is regular at P. Okay, regular at P. So it's really the same thing we did just now, right? So what do we do? We just define regular function, but we haven't collect them together. But now we collect them together. I can collect them and then let them form a ring. Okay. Are you convinced that it is a ring? If there are two things is regular there, you add them together, still regular, multiply them, still regular. Okay. So proposition here, some of it is easy to understand. So the local ring actually is a subring. Okay, so if you can write it as a representation, right? So if you add them together, you still have the fraction representation, the rational representation. Okay, so it's a subring of KV. And moreover, I think this next sentence is quite useful here. OVP here is equal to what? K of V times H inverse of HP not equal to 0. Okay, this one I think is quite interesting here. So just now we only have one H, right? Now you put different H together. And then why is it called local ring? Okay. Okay, maybe from the construction is local, but there's another definition that algebraic make based on this ring here. Okay, actually you can prove that this ring only has a unique maxima ideal. So can you think of what is the maxima ideal here, the unique one? Meaning, if you have any larger one, it should be the whole ring already. So usually you call it MP, right? Can you think of what is it? What's the unique maxima ideal here? Yes. Let me think. Yeah. 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 I think I'll join a lot of things here. It makes sense. Yeah. Okay. So MP here. So what are these things here? where are the elements from? For first of all, where do we pick this element from? All VP pick from where? Function field. Okay, so obviously these elements are coming from function field. And then what's the property you need to satisfy here? Actually, you need to require FP equals to be 0, and then GP is not 0. Okay. So how do you show that a ring has this unique maxima ideal? Just now I say a property of maxima ideal, right? If you go a little bit bigger, it will become the whole ring. Okay. One thing you can show is, last time we also showed that if you have a ring quotient by maxima ideal, you get a field. Okay. So, so what's the thing you can use here? So one thing you can do is try and show that. So I think first two you can try it out. For the last one, let's say this is 1, this is 2, this is 3. So for 3, what can you do is, if you look at OVP slash out MP here, well, you can show that these are all unit in or VP. Okay, these are actually unit of VP. Why? If you look at everything outside MP, it should be a unit. If it's living outside MP, right, meaning what? MP is not 0. Okay, if FP is not 0, then you can take the inverse. Okay. Okay. So here as F inverse is not living in OVP if FP is 0. All right. Okay, so motivated by this local ring property here, we'll define a more general local ring. So define a more general notion of local ring, which is called, can I say which is called? It is also known as a localization of rings. Okay, so there's a natural way, okay, to make your ring into a local ring. Okay, so having a unique maximal ideal. Okay, so what do we do here? First of all, we're going to define something called the multiplicative system. Multiplicatively system in a ring R. The non-zero subset. Okay, first of all, non-zero subset. Wait, what's this R here? This is the ring R. Be confused. Okay. With following for property here. Okay, so first property is if A and B is in X, then AB must be in X. Okay. Second is identity is in X. Okay, then we will say that X is actually multiplicatively closed. I think this property looks familiar, right? Does it look familiar or not? Prime ideal says what? When is an ideal prime? A AB in X implies A in X or B in X. Okay. Okay. Is a opposite of this statement one. AB in X, A in X or B in X. Okay. But if you take the contrapositive, contrapositive of prime ideal, what do you get? A not in X, B not in X imply A, B not in X. Because this in or not in, you can consider as a complement, right? If A not in X, B not in X, all means what? A in the complement of X, B in the complement of X implies that AB is in the complement of X. So meaning what? If you consider a contrapositive, the complement of a prime ideal become a multiplicative Lie system. Okay. Okay. All right. There are a few examples you can prove. Okay. So the first example, a ring is an integral domain if and only if the non-zero element in R is actually multiplicatively close, which is a multiplicatively system. Okay. Okay, so how to prove this? I think it's a very quick proof here. So if you take A, B in R, okay, take A, B in R, if you take A, B in R, if and only if, so take A, B in R, then A, B not 0, if and only if A not 0, B not 0. We do the other way. Which way? This way? Not 0, okay. Then Rx is a multiplicatively closed set, is it? Okay, so anyone get this or not? Are you confused? Confused? So this sentence actually proves everything already. Huh? 哎呦，很奇怪哦，为什么啊 ？Why? Why? So we go through the usual statement, right? Left to right, right to left, right? Okay. So if you want to go from top to bottom, you take two elements non-zero, right? Put them together, it should be non-zero because it is the integral domain. Integral domain says what? A, B equals 0, either one of them to be 0, right? Both of them not 0, then the product is not 0. And then you go the other way around, should be the same. Okay, same. This if and only if just say that if you want to define okay, well, so wait. So first definition is A, B. Okay, let me write it down. So the first definition is, okay, how should I put this? Okay, A, B equals 0 implies that A equals 0 or B equals to 0. Okay, now is this sentence here, if and only if A not 0, B not 0 implies A, B not 0. Contrapositive. I don't know. Contrapositive, logically equivalent. Okay, contrapositive. Does it make sense? Okay. Well, obviously, you still have to check another one. One is in there, but I think it's not hard. Okay. Okay. I mean, one is in both of them, so it's fine. This element one here. is in both. Okay. All right. Next proposition here. So this proposition is very important. Please remember, integral domain implies that the non-zero element is a multiplicatively closed set. Okay, very important. Later we'll build on this example. Next example is an ideal is prime. Is prime also if and only if the complement of this ideal is multiplicatively closed. Just now I think we discussed this already. Okay, we discussed this. So left for exercise. Okay. So these two example here give us a very good base on how we define localization. Okay. So please remember, if you don't understand first, please memorize first. Integral domain has something to do with its non-zero element to be multiplicatively closed, and then ideal being prime imply that the complement of this prime ideal is multiplicatively close. Okay. Okay, let's continue. So now let's define. Let R be a ring and S be a multiplicative system in R. Okay, so we'll define the localization. Rx of R with respect to X is defined as Rs to the product set of R cross X. Okay, quotient by some relation here. So what's this relation here? Okay, so this is the usual relation we'll put on fraction. So R prime X prime is equals to R prime prime X prime prime if and only if there exists an S in the multiplicative set system such that X times R prime S prime prime minus R prime prime X prime equals to 0. Okay, so if you heuristically rearrange this, I want to say heuristically because you cannot really do it. Heuristic, how to spell? Heuristic, I searched for the definition before, is every time you do the calculation, right, you think that this kind of writing is useful, but actually it's a illegal writing. Heuristically, okay, 幻想 heuristically, you can rewrite this as what? So okay, let's do it step by step. X R prime X prime prime equals to X R prime prime X prime. Okay, which is equals to what? R prime over, sorry, X prime prime. Okay, which one we want to leave it? X R prime over X prime equals to or R prime prime over X prime. Okay. I think I didn't write this relation wrong. Did I write this relation wrong? Is this what you do for your fraction or not? How do you declare that? Okay, so let's put here how to declare that 1 over 2 equals to, let's say, 2 over 4. You need to mention something about 1 times 4 and 2 times 2. Okay, let's say we do something more. 4 over 8. So what's this S doing? Suddenly I can't recall. The S here is just 1, right? Quite trivial. Do we have a non-trivial case? Do you have any non-trivial case? Seems like not. Oh, this is a field, so we can just cancel it, right? But here, remember that here is a ring, right? So we cannot just cancel S on both sides. And so we have a more general equality. Okay. Okay, well, next. So how is it a ring? So let's put here. How is it a ring? Well, the ring here is actually quite similar on how we build the field of fraction. Okay, quite similar to how we build a field of fraction here. But field of fraction there we consider S to be, no, we consider R to be integral domain. Okay, and then what do we do here? There, we literally take any element in integral domain to be our denominator. Okay, but in this case here, the thing that we are allowed as a denominator here is actually the denominator actually as a multiplicative system. Okay, those things in the multiplicative system. So actually it's a generalization of field of fraction. Okay, it's a generalization of field of fraction. Okay, so I'll say that next theorem is prove that RS is a commutative ring. Okay, so I'll put here similar to field of fraction of R if R is an integral domain. Okay, it's really similar. So let's see. Let's see. Example. Okay, let's look at example here. So first example is obviously the field of fraction of integral domain. Okay, so if you have a integral domain here, R as an integral domain. So what is the localization? Okay, localization of R on the non-zero element there. Okay, this is actually the field of fraction. Okay, field of fraction here. Where Fr is the field of fraction. Okay. So in the field of fraction definition, right, where do you localize it? Actually, you localize on the non-zero element. When you don't include the zero, right, you cannot divide by zero. Okay, the other thing is another places you can localize is prime ideal. Okay, so if you look at P, right, prime ideal. Okay, where's the multiplicative system here? So the multiplicative system that we've proven here is take the complement. Okay, you take the complement of this prime ideal here. Okay, and then we will write the localization of ring on the prime ideal as R on SP. Okay, and then we will call that R localized at P as the localization of R at P. Okay, so the notation here is a bit confusing. You might think that, oh, RP, I use P to make my denominator. Actually, it's not. Okay, you take the complement of P, and then those are your denominator. Okay, I think, yeah. 哪里 Which one is 什么啊？这个RSP RSP 对 RSP， 这个是正常的。Normal Okay, RSP. So, I mean, well, I think this is the first place. If you are a newbie reading Hearthstone, then maybe you'll get stuck here. I'm one that gets stuck here last time. But be sure this RP here. Okay, it's not localizing. It's not using P as a multiplicative system, but using a complement of P. Well, so actually this is a local ring. Okay, so meaning, let's define it. So let's define now what's a general local ring means. So a local ring is a ring that has a unique maximal ideal. Okay, so the claim is position. The localization of a ring is a local ring. Okay， 有点绕啊。都明明把它 localize 了，怎么还要问我是不是 local ring？ So what is a local ring? What's the unique maximum ideal here? Again, where should you pick these? Where should you pick the element from? Where should you pick the element from? These are picking from the localization. Okay, so in localization, we heuristically cannot heuristically anymore. Just write it as P over X. Because after we're proving it as a commutative ring, right? So we can denote this notation here. So what's the property that need to be satisfied by this element here? It's really similar to how we prove the local ring at a point. Okay, so what do we do there? We make sure that the numerator evaluated at P is 0, but the denominator is non-zero. By this case, what property replaces the zero non-zero thing? Whether you are in the prime ideal or you are in the complement of prime ideal. So which one should be in the prime ideal? So previously is Fp equal to 0. Now, so which one? So the numerator have to stay in P, and then S need to stay in SP. Okay. So the claim is this is a maximum ideal. Similarly, same proof actually. You need to prove that the complement of this MP should have a unique. Yes. Is it Rx? Oh, sorry. So, is it what? Rx. Oh, sorry. I mean RP. XP. Yeah, correct. Okay, so try show that. MP C consists of unit. Okay, similar proof to what we had just now. Okay, another examples. Can we get to structure shift before we finish? Cannot. Alang, 2 more pages. Very fast. 2 more minutes. Okay, let's do it in 2 minutes. Okay, so the third thing you could consider is if you consider your SF, okay, let your SF to be F to the N. Okay. Obviously, this is a multiplicative system because you just take F, multiply F together, power F multiply together, you still get power F. And then you can try and localize your R on this F. So what does it mean here? So meaning you localize your R on at the complement of F. So in fact, you can prove that this is actually equals to R adjoint F inverse. Okay, which is some sub-ring of your pure fraction. Okay. Since what time? 2 minutes. Okay. And next proof. Position. So just now we show that our OVP, right? OVP is a local ring. So can we realize it as some localization or not? Okay, can we realize it as some localization or not? Okay, if we can, what's the ring that we need to consider? So obviously, you localize with this ring of KV, but what's the multiplicative set, multiplicative system that you need to consider here? Okay, let's call it a MP, something to do with MP bar. Okay, so what's MP bar here? So let's for a point P in V. So we're going to define MP bar to be all the function in KV such that FP is 0. Okay, because you need to look at the complement of this thing. Correct or not? You need to look at the complement of this ideal here. Okay. So since I put MP here, right? So meaning this MP is not just prime, I think it's also maximum. Yeah. Okay, you can try and show it. Okay. So why is it I put MP bar here? Actually, the maximum ideal inside this string is the MP. So there's a relation between the MP that we defined just now with this MP bar. Just replacing this KV here to OVP, that's all. OK， OK， 好了，要好了，要来了，最重要的东西要来了，最重要的来了。OK， 要完了，要完了，结束了。Okay. So for every open set here, we'll define what we wanted to define just now, O of some open set. Okay, so what's this O of some open set here? Actually, it's O on every point in V, okay, on this open set. This is defined to be all the function in KV, so in the function field, sorry, such that F is regular on U. Okay, also, if you want to check this OV on empty set, because empty set is also open, right? Okay, so we need to define it. This O for every open set. Then this is a 0 function. Okay. So the proposition you can try and prove is this set is a ring actually. Okay. So in algebraic geometry, right? Whenever you see O something, almost they refer it to a ring. Okay. And then moreover, you can show that this is actually a K algebra. So what's a sheaf then? Okay, last level. So what's a sheaf? So the set of rings, not just consider one ring, the set of rings, because I give you one open set, we will have a different regular set already. Okay, so this set of ring together with something that we call the natural restriction homomorphism. Okay, maybe this name is a bit fancy. It's just saying that the opens between open set, right, there will be a map. What's the map between open set? It's just inclusion map. Okay, so the natural restriction homomorphism. Well, this thing together will form something called a structure sheaf. Structure sheaf. OV. Okay, so the natural sorry, 有点多话给我讲一下. So if there's a remark here, if you have a map from U to W, right? So it's a subset. Then this O will go the other way also. Okay, you can prove it. You can prove it. Okay, I think stop is not enough if we don't finish at, sorry, shift is not enough if we don't finish at stop. So last 的 last 了，真的很 last 了，真的很 last，真的很 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 last。OK， so 没有，真的没有，我等下也要出去了，所以我也是赶时间其实，但是为了你们我留下来。OK， so OVP here is actually called the stock. It's actually called the stock. Do you guys have idea on what sheaf and stock is? You ever learn this in your English language life? 没有咩？真的没有啊？ Maybe next time we can make a trip to Kedah or Sekinjang, a place in Malaysia. That 种稻田啊。Yeah. So sheaf is something. Sheaf 是sheaf is a bundle of bundle of 稻田叫吗？忘记写了，英文叫吗？ Wheat. Yeah. Bundle of wheat. Correct. I think so. Bundle of wheat. Okay. So sheaf is like this. You bundle it together. Okay. But stock is just one piece of it. 翻身那里，翻身 jump。OK， 你没有看过，所以 it's okay. Okay. So yeah. So you have a sheaf. Okay. Inside the sheaf you have a stock. On the stock you have a jump. 对吗？你的那个稻田是从种子传嘛 germinate. So you have a jump on the stock here, and if you put the stock together, it's a jump. Right, stock is on the P in every point. Okay, but obviously you need to apply on the open set first. In different open set, maybe give you a different set of regular function. But in the end, what this OUR or VP give you is a regular set of regular function. Okay. Okay, that's all. See you next week. Yes. 什么？这个。Yes.
Finite algebra A 啊，B 一定要在 A 里面吧？
Finite P algebra A B 一定要在 A 里面，一定要，因为你的 A 是等于 B 乘 linear combination of B 嘛，连它就 B 一定是活在 A 里面啊。
Finite generator。
喂 ，Finite generator 什么 ？Finite generator algebra，哎呀，不是 Finite generator algebra 只是说 A 等于 A。A
等于 join
B 咩？要用 B 咩？
Finite generator 是这样吗？
哦呀，对。
那 B 一定要在 A 里面没有？
肯定也在里面呢，都在里面呢，没有问题。重点是它的写的方式不一样。这里写的方式是说每个 A 里面的东西都写成 linear combination，那这里的东西是这里的 polynomial， 它写法不一样嘛。
就它 generate 的方法不一样
啊，对，
但是我在这个
写法
我在这个 A 里面哦，也是有3个 law composition。
这个 A， 这个 A， 这个 A， 这个 A， 这2个 A 都一样的，
就是里面
它自己有乘法啊，自己有自己的乘法。现在只是说这里面的东西怎样写成这2个形式。
所以其实在这个里面，这个比它还要，这个比它还要 generate。
应该我觉得。
这个里面有 power 哦，
我觉得不，可是不，哦，你 fix A 哈，可是我觉得好像他们不是 subset of each other，那应该不是 subset of each other，他应该不是 subset of each other 吧？我觉得。
他都说，不 finite algebra，其实他的意思是，他把 finite algebra 当成 finite algebra。